नमस्कार, सुस्वागतम, केम छो, आदाबार्स, वेरी गुड आफ्टरनून। आप सभी का पीआरएल के अमृत व्याख्यान में स्वागत है, अभिनंदन है। ए वेरी वार्म वेलकम फ्रॉम मी अनिल भारद्वाज फॉर द पीआरएल का अमृत व्याख्यान। टुडे is the 60th Vyakhyaan of the 75 episodes series of Vyakhyaan, which is being organized as a part of PRL's 75 years of legacy and history in fundamental physics and space sciences. Today's Vyakhyaan is also special because it is being held as a part of Udaipur Solar Observatory's Foundation Day lecture. Established in the year 1947 by the father of Indian space program, Dr. Vikram Sarabhai, the PRL's Platinum Jubilee coincides with India's 75 years of independence. Hence, it's a joint celebration of the development of science and technology in India by PRL under the banner of PRL Amrit Vyakhyaan. Today, we have yet another very distinguished Vyakhyaan and a very special invitee on the occasion of the celebration of US Source Foundation Day, Professor Kazunari Shibata, who is emeritus professor at Kyoto University in Japan, as well as distinguished visiting professor at Doshina University in Japan. And he is going to speak on threats of the sun and superflares. We greatly appreciate and thank Professor Shibata for agreeing to our invitation and to be with us today at the special occasion of PRL Amrit Vyakhyaan and USOS Foundation Day lecture. This is being celebrated as a part of PRL's Platinum Jubilee as well as Azadi Ka Amrit Mahotsav. I now request my colleague, Professor Nandita Srivastava, to kindly formally introduce our today's Vyakhyaan Karta, Professor Shibata, to all the members on the WebEx panel, as well as those who have joined us live at PRL's YouTube channel. Over to you, Professor Nandita.
Thank you, Professor Bharadwaj. It's indeed an honor and privilege for me to introduce Professor Shibata as the speaker of the Vyakhyaan that is being organized today on the occasion of the 47th Foundation Day of the Udaipur Solar Observatory. Professor Kazunari Shibata is currently an emeritus professor at Kyoto University. He is also a distinguished visiting professor at Doshisha University in Japan. He obtained bachelor's and master's degree both in astrophysics from Kyoto University, and he also has a PhD in astrophysics from Kyoto University. He later served as research associate and then as an associate professor at the Aichi University of Education. In 1991, Professor Shibata moved to the National Astronomical Observatory of Japan, and in 1999 became a professor at Kwasan and Hida observatories of the Kyoto University. He was the director of Kwasan and Hida observatories at Kyoto University from 2004 to 2019. In fact, Kwasan and Hida observatories have a long history of solar chromospheric and photospheric observations and also of magnetic field measurements, which are similar to that we do at Udaipur Solar Observatory. Very interestingly, Professor Shibata began his scientific career with the research focusing on active galactic nuclei and then shifted to solar physics, where he made significant contribution to the studies of jets and solar flares. Professor Shibata has played a key role in the Japanese Yoko and Hinode solar missions. Through his research contributions, he has led the international research cooperation on space weather forecasting system. Professor Shibata has been conferred several awards. One out of these, I would like to mention a few. He is a recipient of the 2001 Chushiro Hayashi Prize of the Astronomical Society of Japan. In 2019, he was awarded the Chandrasekhar Prize of the Association of Asia Pacific Physical Societies Division of Plasma Physics. And in 2020, Professor Shibata won the prestigious Hale Prize from Solar Physics Division of American Astronomical Society for his outstanding work on the properties and behavior of magnetized solar and astrophysical plasmas. In 2009, he received the NICETEP Award of Japan for achieving outstanding results in the science and technology. Along with his scientific research, he is also committed to public outreach. He has written a popular book named as Taiyo no Kagaku, The Science of the Sun, in 2010, for which he won the Kodansha Science Publication Award of Japan. Professor Shibata has served as Vice President of the Astronomical Society of Japan during 2009 to 2010, and also as its President from 2017 to 2019. With this brief introduction, I would like to invite Professor Shibata to deliver his talk on a very catchy topic, Threat of the Sun and Superflares. Professor Shibata, please.
Yeah, thank you very much for inviting me to this wonderful lecture event. And at first, I'd like to say congratulations for 75 years anniversary of Physical Research Laboratory of India. And as a solar physicist and astrophysicist, I have known active research in Udaipur Solar Observatory and as well as space science led by ISRO. And so I'm very much impressed by recent development of ground-based and the space science led by PRL and as well as various physical research. So once again, I'd like to thank you for inviting me to this occasion. And can I start my lecture?
Yes, please. Yes, we can start sharing.
Excuse me. Wait a moment. Sorry.
It's fine.
It's
I
okay.
hope you have checked the audio with the audio.
Yeah, I checked,
Yes.
so it's okay. Okay. Let's begin my talk. The title is Threat of the Sun and the Superflares. The first flare that human beings observed is called the Carrington flare. This was observed in 1859 by Richard Carrington in England. Also independently observed by Hodgson. This here is a famous sketch of Carrington flare by Carrington. You see, this is a very big sunspot, and you can see this white patch. This is evidence of a flare, now called white light flare. And Carrington noticed this brightening continues 5 minutes. And next day morning, very bright aurora appeared at many places on the earth, such as Cuba, Bahama, Jamaica, El Salvador, and Hawaii, even in Japan. And this was the largest magnetic storm in recent 200 years. And this is a very old days, but human beings already started telegram system using electricity. And such a telegraph system all over Europe and North America failed. And telegraph pylons threw sparks, and telegraph paper spontaneously caught fire. So such kind of some disaster occurred even at this time. And this is telegraph pylons. And on the other hand, more recently, 1989 March, big magnetic storm and aurora occurred in North America, and that lead to Quebec blackout. This is a Quebec state in Canada because of a trouble of a transformer. And also here you can see some transformer was broken because of a very strong electric current induced by this magnetic storm. And this magnetic storm was as large as 540 nanotesla, and this was produced by a big solar flare, X-class flare. But this is not a very big solar flare, so such kind of flare can occur even this year or next year or so. And this is a image of aurora observed from space. So you see that aurora can be seen not only in Canada, but also all over the United States, even Florida. So the question, will the Carrington-class flare occur again? If the Carrington-class flare occur now, what will happen? A recent paper estimates potential damage to the 900 plus satellites currently in orbit could cost between $30 billion and $70 billion. Question, why do solar flares produce magnetic storm on the Earth? What is a solar flare? Will our sun produce superflares which are much more energetic than the largest flare we observed before? Today in this talk, I will answer I will talk about my answer to these questions. So the plan of my talk that follows, and I finished introduction. So let's talk about solar flares. This is the sun observed with visible light called photosphere, whose temperature is about 6,000 Kelvin. And you can see several bright dark spot called sunspot. Okay, sorry. And this sunspot is very important. Sunspot is a source of solar activity and flares and so on. This is same sun observed at the same day, previous image, but observed with the H-alpha line of a hydrogen atom. Then we can see the layer, upper atmosphere of the sun called chromosphere with a temperature about 10,000 Kelvin. And you can see the appearance is quite different from visible surface photosphere. And you can see that near sunspot, bright region are seen. These bright regions called plage, but actually we now know these bright plages consist of very, very small flares now. And also you can see some dark filaments. This is basically the same as a prominence outside of the limb. These are also important feature and a place where the solar flares occur. And what is the actual physical property of sunspot? as you see, sunspot is basically the same as big magnet. And sunspot is born as two spots correspond to N and S polarity of a magnet. And this is a bar magnet with sand iron. You can see some lines. This corresponds to magnetic lines of force. And actually, if we observe sunspot with the H-alpha filter, then we can see similar structure connecting a lot of lines or filament connecting two spots, very similar to magnet field lines. And this is a very good example of a very large flare, X-class flare, observed at HIDA Observatory of Kyoto University using H-alpha filter. And here is two spots correspond to N polarity and S polarity. And you can see also flare brightening occurs two parts, again corresponding to N polarity and S polarity. And actual time scale of flare is more than 1 hour, but here shortened in a very short time scale, so that we can see the change of flare structure, so on. And in the mid-20th century, it was found that the magnetic energy is a source of energy of flares, as we already discussed. And the size of a flare is from 10 to the 9 to 10 to the 10 centimeter. Time scale is from 1 minute to 1 hour and more. And total energy is 10 to the 29th to 10 to the 32 ergs, corresponding to 10 to the 5th to 10 to the 8th hydrogen bombs. So huge energy is released. Mechanism has been puzzling since 19th century until recently. And often prominence eruption occurred in association with the solar flares. And this is actually the biggest prominence eruption in the history, observed in 1946 in HAO of the United States. And once again, you can see the helical structure in the prominence. This is an important property of prominence eruption. And from 1991, X-ray observation, continuous observation started by Yoko satellite, Japan, US, and UK international collaboration project. And I was involved in this space project. And you see, this is solar corona observed in soft X-rays. Solar corona, the same as outer part of the solar atmosphere called corona. And you can see that solar corona is full of flares, explosion, and also ejections, mass ejections. And I was much shocked by watching this one. The solar corona is much more energetic than had been thought. Many solar physicists also was very much impressed by this movie. And the sun is a very dangerous astronomical body. Actually, this X-ray observation revealed that the temperature of the corona is from 2 million Kelvin to more than 10 million Kelvin in the solar flare part. And furthermore, SOHO satellite launched from US and Europe succeeded to observe outer solar corona by this one from space. This circle is a sun, and dark circle is occulting disk. So we can see artificial eclipse. So we can see the corona and also many stars. And from this, we can immediately notice that the solar corona is flowing continuously out to outside. That this is called solar wind. And also once or twice or third times in a day, we see ejection of a gigantic gas plasma called coronal mass ejection, or CME. These coronal mass ejection is a consequence of a prominence eruption or filament eruption from the solar lower atmosphere. So these are very important, especially causing a lot of trouble, disasters on the Earth. Velocity is from 10 to the 1,000 kilo per second, and mass is from 10 to the 15 to 10 to the 16 gram. And I'm sorry, I'm showing the Japanese newspaper, but even if you cannot read, you can see this image. This is a newspaper reporting a very big flare occurred near the center of the sun. And from this flare, very fast coronal mass ejection occurred and collide the Earth and produce a lot of trouble, such as trouble of artificial satellite and radio communication with the ships. Electricity blackout occurred in northern places, and radio communication trouble occurred, and all rise sea. This is okay, but even inside the airplane, the people can receive some radiation dose, a bit dangerous. And why aurora occurs? This was made by NASA to show how a solar flare produces aurora. Flare occurred and coronal mass ejection occurred. Then 1 or 2 days or 3 days later, mass ejection collide with the geomagnetosphere, and finally, energy is flowing the northern and the southern part, generating beautiful aurora. Well, this aurora is very wonderful, but simultaneously, a strong electric current is flowing in the aurora region. That is the cause of electricity blackout trouble. And this is the observation by stereo satellite launched from United States. And amazingly, we now see from the sun to the Earth how coronal mass ejection and blast waves attacking the Earth. So these phenomena lead to magnetic storm and various hazards on the Earth. So now space weather prediction is an urgent issue of human beings. So this figure summarizes various effects of a solar storm on the Earth made by NICT of Japan. And basically, solar flare, CME, and the coronal hole produce three different kind of physical process. One is energetic particles and flare, X-rays, and UV, and the solar wind disturbance. And these three different kind of physical phenomena come to the Earth with a different time scale like this, and finally produce a lot of trouble, satellite, artificial satellite, and astronaut exposure, and on the ground blackout, radio communication, and so on. Sorry, this is a better summary and showing the different time scale and actual consequence on the Earth like this. So the prediction of a solar storm, space weather, is an urgent issue. And now, from now, I'd like to show you more example of solar flares and the prominence eruption, coronal mass ejection, with the music made by Kitaro-san, musician actively working in the world. This music is actually representing the ancient hypothetical monster called Orochi. So very suitable for solar flare and prominence eruption. This is again a very big solar flare observed in H alpha at Hida Observatory. This is a sunspot evolution of sunspot shape, and observed by Hinode satellite. And now energy is accumulating near sunspot, and finally very big flare occurs. And as I said, when solar flares occur, often prominence eruption occurs. This is a very old observation, more than 30 years ago, observed at Hida Observatory. You can see that very large prominence eruption. By the way, this castle is the size of the Earth. This is a solar corona observed in soft X-rays observed by Yoko satellite. Okay. This is when the sunspot number is small, so X-ray is relatively weak. But when sunspot appears, we see a lot of flares occur from X-ray here. But sunspot number change roughly with the 11-year cycle, and this is when the sunspot number is maximum, called solar maximum. And you see that solar corona is full of solar flares and mass ejections. And also we can see that there are many loops, all elementary structures, magnetic field lines, magnetic structures. And this is artificial eclipse observations showing solar wind and coronal mass ejection. This is a famous, very large flare observed by Place satellite launched from US in extreme ultraviolet. And as you see, solar flare loops arcade gradually becoming larger and larger. Also, you can see sometimes white dot appear. That is the evidence of the energetic particles bombarding CCD camera of the telescope. And this is near sunspot, near the solar rim. You see many small flares, mass ejection called jets appearing, observed by Hinode And this is also a famous aurora filament eruption, and the bright region is the flares, and also a lot of energetic particles, protons, bombarding CCD camera. This is the size of the Earth. This is a famous prominent eruption and flares observed by SPO satellite. And this is a very interesting, strange. Prominent material fall into the surface of the sun because of the strong gravity of the sun. A same prominent eruption in a different EU. You see that falling prominent plasma collide with the surface and show brightening. And also the same maybe again you can see a propagation of waves from prominent eruption. These waves are shock waves, so similar to tsunami wave. And this is the largest prominent eruption in the history, observed in the United States 70 years ago. So again, we see that helical structure is the main structure. In some sense similar to tornado, but this is the magnetic structure. This is a more recent prominent eruption observed by Inode satellite. And again, a lot of plasma is falling because of the strong gravity of the sun. This is a big layer observed at Hida in H alpha. This is the same flare in EUV, extreme ultraviolet, by SPO satellite. And you see, this is the sunspot region and prominence eruption, but and brightening is just flare. This is the same flare and the prominence eruption observed in H alpha at Hida altitude. So comparing both, we can analyze the flare physics. And this is a continuation of the prominence eruption. This flare, so coronal mass ejection. So prominence eruption becomes coronal mass ejection. And this is another event. This is that blast wave attacking the Earth as the night. And this is X-ray, X-ray movie of the solar corona again. So you can understand how the sun is active and very dangerous. Okay, and if you want to see the same movie again, actually you can buy this DVD on Amazon. This DVD contains not only the solar movies, but also stellar and galactic movies and aurora and so on. So actually, this can be a good textbook of the astronomy and the space science. So what is the solar flare mechanism? I briefly explain. Solar physicists considered the standard flare model from 1960s like this. Before onset, filament, dark filament or prominence is floating by the effect of magnetic field. These lines are magnetic field. And after eruption onset, this filament and magnetic field start to rise, but this can stop at some height. In that case, we have only confined flares, brightening. But there is a possibility that the filament eruption continue to outside of the sun. And this is a case of ejective eruption. And during this process, anti-parallel magnetic field meet and reconnection occurs. Then huge energy is released to downward and upward. This is called magnetic reconnection. This is the standard flare model from 1960s. But actually, physics of reconnection is a very difficult problem, and there is not enough observational evidence of reconnection. So many great solar physicists doubted this flare model until 1990s. But after Yoko launched, Yoko satellite discovered evidence of magnetic reconnection using simultaneous H-alpha and X-ray observation of a flare. And then you can see that loop, especially with a very strange shape we call cusp. Cusp-shaped flare occurred just above H-alpha 2 ribbons, connecting two ribbons. This is actually predicted structure by such standard flare model, magnetic reconnection model. So therefore, at least phenomenologically, magnetic reconnection model has been established in 1990s by using Yoko data. And I myself also studied the flares using Yoko soft X-ray data and found that plasmoid ejections are ubiquitous in flares, from small impulsive flares, long duration flares, and even the very big coronal mass ejections from giant arcade. Spatial scale is very different from 10 to the 9 centimeter to 10 to the 11 centimeter, but basic magnetic structures are very similar, common. And I start to propose unified model of solar flares, including plasmoid ejection or filament or prominence eruption. These eventually become coronal mass ejection. And at the surface of the sun, we see a very bright X-ray loop and H-alpha ribbon and other X-ray emission and so on. So I call this plasmoid-induced reconnection. This plasmoid ejection is a key to understand the physics of solar flares and mass ejection. And as for the space weather relation, I should explain that when the prominence eruption or coronal mass ejection occurs, we have a shock wave ahead of eruption or CME. And at a shock wave, a lot of energetic particles accelerated, and then eventually attack the Earth and the astronaut and so on. So solar energetic particles are also directly accelerated from a solar flare. But in the case of a very strong CME occurs, more energetic particles, protons and electrons accelerated, attacking the Earth. So I'd like to discuss the third question. Will our sun produce superflares which are much more energetic than the largest flare we observed before? So this is statistics of occurrence frequency of solar flare, microflares, nanoflares. Vertical axis is the occurrence frequency, and the horizontal axis is flare energy. Also, here corresponding to X-ray flux, X-ray class of solar flares. And here is the largest solar flare observed in the history. Carrington flare is probably around here. And the question is, do we have super flares, more energetic larger solar flare? So if here you can see this is a very beautiful frequency statistics. That is, when the energy become 10 times, then the frequency, occurrence frequency decrease 1/10. So we have very beautiful power law distribution of flare statistics. And this is quite similar to earthquake statistics, interestingly. And so we can suppose if this statistics law continues to even larger flares, then super flares with 10 to the 34 erg may occur once in 100 years or 1,000 years or so. Flare occurrence frequency is very low. But if such a super flare occurs, that will be very, very dangerous for our civilization. So this question is important, I think. And I also thought that super flare may have affected life in the past on the Earth, because of in a very long history of life on the Earth, we know several times mass extinction of life occurred, and super flare may be a cause of extension of life. So, and I started to think about such possibility, and found that X-ray astronomical observations revealed that young stars show super flares with 1 million times more energetic than the larger solar flares. And so at least we can say that in a very young era of the sun, we have such a huge super flare. Very, very scary. So we can ask, can super flares occur on the present sun? But fortunately, the sun is not young, already 4.6 billion years old, and slowly rotating. This is important. Rotation is a key to understand the activity of the stars. So that it has been believed that the sun would not produce super flares, according to Dr. Schaefer. However, amazing discovery was made in 2012 by Maehara et al. In a Kyoto University group, my group. How can we observe super flares on the sun? If empirical statistics rule of solar flares is applied to much larger flares, such as super flares, then the frequency of super flares with energy 1,000 times larger than the larger solar flares might occur once in 10,000 years. However, the period of modern observation of the sun with telescope is only 400 years. How can we observe the sun for 10,000 years? So I was the director of observatory, so I thought the star is useful, stellar observation. If we observe 10,000 solar type stars similar to our sun for 1 year, we can get the data similar to the data obtained from 10,000 years observation of the sun. So I started to discuss with the many astronomers, stellar astronomers. Then Professor Sekiguchi of NAOJ kindly told me that the Kepler satellite space telescope is taking such data. Kepler satellite was launched from NASA this is a space mission to detect exoplanet by observing transit of exoplanet. And this is actually a 95 centimeter space telescope, and has been observing 1600, 160,000 stars near Milky Way for a few years. Among them, roughly half solar type stars. And 30-minute time cadence of visible light data, public, open to the world, fortunately. So this can be useful to detect superflares, very rare superflares. Actually, this Kepler mission is a very successful mission to observe many exoplanets, more than 3,000 exoplanets, and also including planets similar to the Earth. And many, almost all astronomers try to detect brightness decrease because of transit of exoplanet. But if superflare occurs, brightness may increase a little. So hence we began to search for superflares on solar type stars using Kepler satellite data, which include 83,000 solar type stars. So many data included, but number of superflare must be small. And I wanted to collaborate with the young postdocs of our observatory, but they are astronomer, well educated astronomer. They didn't believe in the occurrence of superflares on solar type stars, unfortunately. So I didn't find good collaborators. But one day I had an idea. In the case of a first-year undergraduate students, they have a lot of time, free time, and they may help analyzing these stars because students have a lot of free time. So in physics course, I at that time I taught the electricity introduction to electromagnetism. Then 5 students came to me, and they started search for superflares. And surprisingly, they found 365 superflares on 148 solar type stars. Solar type stars, the G-type main sequence stars. And finally, the data was published in Nature 2012. Please remember, this research started 2010. And finally, the paper was published in Nature 2012, including those undergraduate students. And this is a typical example of a solar flare observed by Kepler. Vertical axis is the brightness of a star and the flare in unit of average brightness of a star. And so 0.01 is 1% brighter than average. Minus is 0.01 is 1% darker than average. This horizontal axis is the time in unit of a day. So this is roughly 30 days. And you can see on average, stellar brightness itself change with time with 1% amplitude. And sometimes you see some spikes. These are superflares. This is the largest superflare in this case, and stellar flare brightness is about 1.5 brighter than average stellar brightness. But by the way, Carrington class solar flare shows also brightness increase, but amplitude is 0.01%. But this is 1.5% brighter. And also, by the way, this is a visible light, so white light. Duration of flare is 0.1 day, so 2 hours or so. So much longer than Carrington flare duration, 5 minutes. And in this case, we estimate total energies of the order of 10 to the 35 erg. This is another event, more energetic. This is 8% brighter than average. Total energy is estimated 10 to the 36 erg. And also stellar brightness period is 5 days or so. And we found that all superflare stars show such a brightness variation. Very interesting. What is the cause of stellar brightness variation? We think it is likely due to the rotation of a star with a big star spot. Actually, undergraduate students also help by calculating stellar brightness change when the big spot is present on stars. And this is a very large spot. Diameter is 10 times larger than the largest sunspot. In this case, stellar brightness itself shows some time variation like this. And this is a very simple model, but amazingly explain real observation well. So this is not a unique solution, but this is only one possibility of brightness change. But modeling is so simple and explain observation very well. So I think this is a very likely possibility. And we are now trying to prove this very big star spot model. And this is a very big X-class flare. This is a white light flare, and actual real observation in 2011 at Hida Observatory. And this is a hypothetical image of a super flare and associated big spot based on the observation. Observe the increase in visible light as well as brightness variation of the stars. So you see that a very big spot must be present to produce a very big flare, super flare. And the next question, can super flares occur on our sun? This is a very recent analysis of all super flares observed by Kepler, analyzed by Notsu and Okamoto. And vertical axis is the flare energy, and horizontal axis is the rotation period of the stars. And as I said, when the stars are young or the sun is young, rotation period is very short, shorter than 1 day or so. At that time, a lot of super flare occurred. But as rotation period decrease, actually with age of stars, the maximum super flare energy is gradually decreasing. And our sun has a age around here. And rotation period is 25 days with respect to the universe. And maximum energy of super flare decrease, but nevertheless, we observe many superflares, more energetic 10 to the 34 erg. By the way, the largest solar flare energy is of the order of 10 to the 32 erg. So 10 to the 34 erg is about 100 times more energetic than the largest solar flares. So such a super flare can occur on such a slowly rotating star like the sun. So this is a bit a scary result. We should remember. And how about frequency? We can plot current frequency of super flare here. And interestingly, roughly speaking, this super flare frequency is on the same power law line. And a bit smaller, but 10 to the 34 erg super flare occurred once in a few hundred years or 1,000 years. And more recently, Dr. Notsu and Okamoto students carefully analyzed all Kepler data and reached the frequency around here. So we can say that super flares of 100 times more energetic than the largest solar flare occur once in 6,000 years. So a bit occurrence frequency becomes smaller than in 10 years ago. But anyway, this is not so different from occurrence frequency. A very big earthquake occurred in 2011 in eastern Japan. So this is not necessarily a future disaster, but can be a present possibility of disaster. Is there evidence of super flare on the sun? Very interestingly, when our super flare paper was published in Nature, related research paper was published in also Nature. That is Miyake-san in Nagoya University and her group discovered a signature of cosmic ray increase in AD 774 to 775 here from 3 rings in Japan, carbon 14. So in 1 year, carbon 14 suddenly increased. And so this is evidence of a strong cosmic ray increase in such year. And at first, they considered the possibility of a supernova explosion near solar system, but there is no such evidence of a supernova remnant near solar system. And other second possibility is a gamma ray burst. But the gamma ray burst possibility has a very low frequency, once in a million years or so. But at this time, that possibility remains. And the third possibility is the super flare on the sun. And next year, Miyake-san discovered another event in 993 here. A bit carbon 14 is smaller, so cosmic ray intensity is smaller, but nevertheless correspond to super flare intensity. And if this is a result of a gamma ray burst, it's impossible. We have 2 events in 1,000 years. So gamma ray burst possibility was excluded. Therefore, now people believe these are super flares on the sun. And very interestingly, Hayakawa et al., young graduate students of Department of Literature of Kyoto University discovered evidence of aurora in the literature, old literature. This is one example, and you see in the old literature, there is a nice sketch of aurora observed at Nagoya near Kyoto. So usually such aurora cannot be seen in Kyoto or Nagoya, Tokyo. But in 1770, this was observed. So this is probably a result of a superflare, comparable with or larger than the Carrington event. And Hayakawa also found literature in Europe. The sunspot sketch corresponding to such aurora. This is a very big sunspot, corresponding to largest sunspot in the recent 100 years. So this is again indirect evidence that superflare may have occurred in very big spots. So if superflare occurred on Sun, what if superflare with energy 100 times larger than the largest solar flare occur on our Sun, what would happen to our Earth and civilization? All artificial satellites would be damaged. All astronauts and some of airline passengers would be exposed to fatal radiation. Ozone layer depletion would occur. Radio communication trouble would occur all over the world. Global blackout would occur all over the Earth, like a Quebec blackout. All nuclear power stations would lose electricity and hence in a state of meltdown, like a Fukushima nuclear power station. So this is the worst dangerous possibility. And as I said, we need to observe solar type stars more using spectroscopic observation, because we have not yet proved that all brightness variation is a result of a star spot. But in order to prove that, we need spectroscopic observations. And in Kyoto University, we have completed Okayama 3.8 meter Seimei telescope in 2018, like this. And this is actually first segmented mirror telescope in Japan, and developed by technology developed by young researchers and engineers in Japan in small companies. And in 2019, October 4, I myself tried to observe stellar flares and successfully observed stellar flare in M-type star EV rock with the help of Dr. Maihara, first author of a superflare Nature paper. And more recently, Dr. Namekata, he was the last graduate student, my last graduate student of Kyoto University. He succeeded to detect stellar filament eruption, evidence of stellar filament eruption on young sun-like star EK Dora. This is a brightness variation of stellar flare. And this is a H alpha equivalent with H alpha intensity. But it's interesting, the intensity itself became less than the average. So this shows the evidence of absorption. And this is the actual line profile of flare as well as post-flare. This corresponds to absorption. This is emission. And you see that wavelength versus time diagram, that is at the initial stage, this absorption has a very large velocity of 500 kilometers per second. But this is gradually decreasing and finally become a positive, means downward falling because of gravitational acceleration. So anyway, this is quite similar to a spectrum of solar filament eruption. So we believe that this is the first evidence of stellar filament eruption from superflare on young sun-like stars. So the important conclusion is that stellar observation showed that very similar property of solar flares. A super flare has a very similar properties with solar flares, but the energy, spatial scale, and so on are very large. Summarizing my talk, using Kepler data, we found many superflares on solar-type stars. Superflares occur on sun-like stars with frequency such that superflares with energy 1 to 4 times 10 to the 34 erg, that is 100 to 400 times of the most energetic solar flare, occur once in 6,000 to 10,000 years, suggesting possibility of solar superflares. This is extremely dangerous for our civilization, as I explained. And these stars have large star spots. Of course, we need to observe more, confirm. There are evidence of solar superflares, including carbon-14 on 775 and 993 by Miyake et al., and old literatures on 1770 by Hayakawa et al. Superflares may have affected the evolution of life on the Earth, as I discussed, and also would affect the future security of civilization and space development of human beings. That's all. Thank you for your attention.
Thank you, Professor Shibata. Thanks for a very insightful lecture on superflares and the possibility of occurrence of their occurrence, and also the impact on the modern society. I think it's time now for conducting the question and answer session, and for this I invite my colleague Professor Ramit Bhattacharya. Professor Ramit, please.
Thank you, Professor Srivastava, and Shibata-san, thank you very much for a very thought-provoking talk spanning the solar as well as the stellar flares. So now we are going to take questions. So initially we will take questions from the participants who are directly attending through the WebEx, and then I will read out questions that come from the YouTube to you. Is it that okay, sir? Is that okay, Professor Shibata? Okay. So now we are formally open to take questions, and I would request, I can see Professor Ambassador raising his hand. So Ambassador, please ask.
Can you hear me?
Yes.
Yeah. Okay. Thank you very much, Professor Shibata, for your very scintillating lecture, which is covering all the way from the sun to sun-like stars, from normal flares to super flares. So I was just wondering, you know, apart from the possibility of super flare-like things happening on the sun, the thing which is confusing me, or kind of forcing me to ask a question about the mechanism, which is probably kind of explaining the super flare like thing, you know, because you of course told about one thing is related to the rotation period of a star. And then also about reconnection mechanism, which is basically one of the mechanisms which we always invoke for flare onset. So whether a reconnection like thing will be possible for explaining the superflare onset also, or something else will be required. So you have anything to throw some light on this?
Yes, thank you for a good question. Yeah, actually, I'm basically theoretician studying magnetic reconnection model of solar flares. And also, such a theoretical model can be applied to stars. And one reason is that stellar atmospheric structure is quite similar. So even for young sun, young sun has a similar photosphere, chromosphere, and corona. And the only difference is the size of spot. So if there is a big spot, all structure become very big. And more and more energy is accumulated near spot, big spot. Therefore, superflare can easily occur based on the same physics that the solar flares show. So, and also I carefully analyze the statistical property of superflares on stars, and that is interestingly same extrapolation of solar flare observed curve. For example, duration versus flare energy is predicted from reconnection model, and that interestingly nicely observed in stellar superflares also. So I believe same physics is occurring in stars.
Yeah. So except for the magnitude mechanism, you expect to be the same. In the early phases when probably the sun also had larger spots.
Yeah.
So
And
that is one.
next question is whether the sun has a large spot or not. This is actually very difficult question because we don't know physics of sunspot formation. That is the generation of magnetic field inside the stars. That is the most difficult problem in solar physics, or maybe in astrophysics also. So that remains as a future important subject. But I think using order of magnitude estimate, using Maxwell equations, my simple calculation showed the possibility of superflares on the sun, slowly rotating sun.
Okay, thank you. Thank you. One more question, if I can ask Ramit,
Yes,
is
please.
yeah. So this is regarding the magnitude of the solar flares in the past, which you reported, so-called super flares, are around 100 times more than the 10 to the power 32 erg-like solar flares, which we normally have, been observing in recent years. But if we consider the other solar-like stars having at least 5 order of magnitude larger flares, which are basically known as super flares as such. So whether there is any possibility of such 10 to the power 37 ergs super flares on the sun ever in the past, or no?
Excuse me, I'm sorry. Please speak in short.
Okay, okay. No, so the question is whether there is any possibility of super flares like what you have reported for solar-like stars, which are having 10 to the power 37 ergs or so, which are 5 order magnitude larger than the solar flares which we know. So in the past, whether such super flares may have occurred in the sun?
Yeah. And your question is more than 1,000 years ago, something occurred on the earth.
That is only 100 times. You said that there are 100 times larger.
Mm.
But by definition, if which I
yes.
remember,
Roughly.
that super flares are 10 to the power 37 hertz. So whether any
34 erg, 10 to the 34 erg.
that's what we have observed on the sun.
Around 1,000 years ago. And with such energy, fortunately, solar energetic particles cannot come to the ground. So all human beings were safe. And in those old days, there is no artificial satellite, no astronaut, no airplane, so and no electricity, no internet, so no disaster in our old civilization.
Okay, anyway, my question was a little different, but I can probably send you my question later. Maybe others can ask further questions to you. Thank you so much, Professor Shibata.
Yeah, thank you.
Professor Harish, you have raised your hand, so.
Hello, Professor Shibata. Am I audible?
Yeah.
First of all, thank you very much for this wonderful talk. I really enjoyed that music with solar flares with music, and we see very rarely that fusion of art and science in the presentations. My question is about this Kepler data, where you saw that there is a periodic variations, and your hypothesis is that this is because of the big solar spot. So if that is the periodic variations is because of the big solar spot, shouldn't be the solar flares be occurring near that when there is a dip into the intensity, whereas when you saw the data, solar flares seems to be occurring where there is a brightness or peak of that curve.
Excuse me, would you please speak slowly?
Okay, my question is about this Kepler data, where you saw there is a periodic variations of the intensity, and that intensity is because of the sunspot, and the sun is our star is rotating around the axis. Okay, if that is the case, because solar flares occurs near the sunspot, shouldn't the solar flares should be near the where there is a brightness dip, because that is the time the spot is facing toward the telescope.
You said solar flares increase brightness.
No, my point is that solar you have shown there is a periodic variations, and that is because of the sunspot or star spots in that data. Okay. So if solar flares are near the spot, black spots, shouldn't that be then the timing of the flares should be closer to the where there is a down into the intensity?
You are asking flares are associated spot?
Yes.
That is another good question. And interestingly or curiously, a statistical study shows no correlation between brightness variation and super flare occurrence. So we have not yet final answer, but one possibility that these super flare stars show have a big spot, and always stellar surface is covered by many spots. So it's not so easy to show correlation between spots and flares. In the case of the sun, spots are very small and not uniform. So we can find a good correlation between spots and flares. But in these super flare stars, very active, so not easy to find correlation. That is my present answer.
Okay, thank you, sir. Thank you very much.
Professor Pallam Raju, please ask your question.
Thank you, Ramit, and thank you, Professor Shibata-san, for this fascinating lecture. As I always enjoyed listening to every bit of it. Thank you very much. My question is, in the formation of the big solar spots, are there any models that talk about the recipe to make the big solar spot, and and do we have some indication of some big solar spot is getting made in the sun, by some other means?
Excuse me, you're asking how to make a big spot?
Yeah, how to make it work. Yeah, what are the theories that say about how is a big spot made on the sun?
Okay. As I said, we have not yet had a final answer on the origin of a spot, even sunspot, still puzzling. But theoretically, many people think differential rotation of the sun is important to amplify magnetic field. In the case of the sun, the equatorial rotation is fastest, and rotational speed is low near pole, north and south pole. So there is a strong differential rotation between equator and pole. And if magnetic field penetrating from north to south, then such a magnetic field is twisted and can be amplified. And of course, that is limited because of such a strong magnetic flux tube rise from the inner part to the surface. And so there is a saturation. Of course, we don't know such physics finally, but if the star's rotation is very fast, then the amplification time becomes short. So that means the possibility to store huge magnetic flux inside the stars. That is the reason why young stars, fast rotator has a big spot and big superflares. But even inside the sun, I estimated how much magnetic flux can be amplified. Then my order of magnitude estimate showed 10 years enough to amplify big spot, make 10 to the 35 super flares.
Okay, good. But then if it takes 10 years, then probably we will have some indication that are there, will there be any indication that something is getting generated? Are there any means to know that?
That is another interesting question. Yeah. If we can find such a signature, how do you say, precursor of big spot or super flares, then that would be very useful to prepare super flare disaster
Yes.
to avoid.
Good. Thank you very much. Thank you very much.
Thank you.
So, any other question from the WebEx platform? Because I don't see any other hands raised. So then we can move on to the YouTube. So Shibata-san, I am going to read out the questions to you.
Wait a moment. How can I read?
I will read it for you.
Mhm.
So, so the question one is from Bhaskar Mukherjee.
Mhm.
He is asking you that could we forecast the space weather by observing the intensity fluctuation of UV radiation from solar flare?
Mhm.
So that is the question.
UV?
Can we forecast space weather from the intensity fluctuation of UV radiation during a solar flare?
Yes, UV fluctuation is very large in solar flares.
Yes. So the question is, can we predict space weather from that fluctuation?
Yeah, I think so. Yes. still, of course, such kind of research is developing, but I think this is a real subject. Many space weather researchers are doing. Yes.
Okay. The next question is, are the low energy solar wind protons accelerated to very high energy by CME shock waves?
solar energetic particles.
Yeah, whether they are accelerated by the CME shock wave.
Yeah, many energetic gigantic events case, energetic particles accelerated at the shock front ahead of a CME. But as I said, even solar flare reconnection region, very high energy particles, protons and electrons can be accelerated. And
Okay.
there is evidence of such acceleration from hard X-ray, gamma rays, and microwave.
Okay.
Yes.
Thank you. The next question is from Vagish Mishra. He is asking, can super flares be a possible solution for the faint young sun paradox instead of unusually high greenhouse gases?
That is another interesting question. Actually, Dr. Ira Petian wrote a paper about such a problem. In young sun, many superflares occurs. That means a lot of energetic particles attacking the young Earth. Then such energetic particles generate a lot of molecules for keeping the Earth temperature. That is, how can I say, warming element, like CO2. So, anyway, such a very energetic particles can help greenhouse effect of the Earth. So that may solve the young sun paradox.
Okay, Shibata-san, the next question is from Professor Hariom Bats. He is asking, okay, sorry, I lost the question. So, yeah, does the reported solar super flares from cosmic ray data and tree ring records, the one that you have shown in your slides, has any very severe environmental effects or not?
A mental effect.
Environmental effect. So whether there is any effect on the environment or
Yeah,
not.
that is another interesting question. Actually, I'm collaborating with the medical doctor of Kyoto
Yes.
University, and he is studying the correlation between solar flares and the number of how do you say self-killing. I'm sorry, I don't know English word, but because of a mental effect,
Okay.
many young people suicide.
Oh, okay.
And there is some correlation between number of suicide and solar flares. So therefore, that is still in a very preliminary stage of research. But to know solar activity may be very useful to keep our health. That is, I think, important direction in future.
Okay, thank you, Shibata-san. The next question is from Professor Ketan Patel. He is asking, do we expect any correlation between the flare and the emission of solar neutrinos?
That is I had I was asked the same question by elementary particle physicist
Yes,
10 years ago,
yes.
but I don't know the answer at present. But if neutrino interact with magnetic field, there may be some physical effect.
Okay, so there are many questions. So I would like to, should I continue? Or because it is going to be 9:30 at your end, I think.
I'm okay.
So, okay. So I will continue with one or two more questions. So one question is, can you comment and clarify again on the edges of the stars on which super flares were observed in the meteorites using short some nucleides? We have in 2019 shown evidence of at least one super flare. So basically the question is, can you please tell it again on the edges of the stars on which super flares were observed? Basically.
Do you want to see the slide?
Yeah, that corresponding slide if you show.
Okay,
Where the,
wait a moment.
yes.
This one?
I think this one because it gives you the, and if you comment on the ages.
Age is here.
Yes.
So this is the present, and this is the unit of giga-year. So
Okay. Yeah.
Except for a very early stage, basically super flare energy, largest super flare energy is of the order of 10 to the 35 erg or so. So
Okay.
not so strong. But please remember, this is based on only 80,000 stars observations. So we have not yet studied the much low frequency super flares. So we need to study more. So this is not the real upper limit.
Okay. Thank you. And the last question is from Hariom Vats, Professor. He is asking you, will younger sun-like stars have more or less differential rotation?
Yeah.
Compared to sun, I think.
Yes. That is another interesting subject to study in future. So from that point of view, spectroscopic observation of stars are very important to reveal the differential rotation of stars.
Okay. So thank you, Shibata-san, for answering so many questions.
Ramit, can I ask one?
Yes, please.
Okay. So, Shibata-san, I had a question regarding the recurrent flares, like when you see on the surface of the sun, when there is a big active region, you can have recurrent flares, and it may occur in the order of duration of days or even hours sometimes. What happens in case of super flares? Since I know that there are studies which show that waiting times of flares is correlated with the magnitude of the flare. Would it be not seen for several hundred of years, or what is your opinion on that?
Yeah, I think similar flaring can occur in stars, superflare stars. But and we already know that in some very active stars, many superflare occurs in a short time. So that is
The
probably
duration. What is the duration of this short time?
そうね、
It's okay. I can
it's better to see this
the
one.
paper. Okay.
This is a very active stars, and you see small spikes,
Yes.
many spikes. So this is evidence of many superflare occurs.
Okay.
This is small but much larger than the solar big solar flares. So, so it would be interesting to study more based on your question.
Yeah.
In future. Yeah.
Yes. Thank you. Thank you so much.
So thank you again, Shibata-san, for answering so many questions. So I would like to request Professor Brajesh Kumar to come in and take the mantle from me. And thank you, Shibata-san. Thank you again.
Thank you very much.
Thank you.
for listening.
Thank you very much, Ramit. And so that brings us to the concluding session of the 60th episode of the PRL Ka Amrut Vyakhyaan series. First of all, I would like to thank Professor Shibata for accepting our invitation and giving this excellent talk on the threat of the sun and the superflares, which has a very important societal impact. It is a pleasure to mention here that this is a special lecture to commemorate the foundation of the Udaipur Solar Observatory. Thanks again to Shibata-san for nicely answering the questions from the audience. And many thanks to all the audience on WebEx and YouTube platforms for attending today's lecture. At the same time, I would like to express my sincere thanks to Professor Anil Bhardwaj, Director PRL, Professor Pallamaraju, Dean PRL, and Professor Nandita Srivastav, Chair PRL Ka Amrut Vyakhyaan series, for their continuous support in successfully organizing the talks in this series. Also, thanks to all the committee members of the PRL Ka Amrut Vyakhyaan series in their efforts for smoothly organizing the talks in this series. Thanks to all of you for being with us in our Azadi Ka Amrit Mahotsav and 50 years of PRL celebrations. So with these words, I propose the closure of today's session. See you again in the next episode of PRL Ka Amrut Vyakhyaan. Thank you.
Thank you very much.